This lesson deals with equivalent circuits. You can find these notes in the ECE201 ebook in Chapter 2, starting on page 25. Circuit analysis can often be made easier by replacing part of a circuit with one that is equivalent or simpler. We'll take a look at quite a few examples later in this chapter and the chapters that follow. Let's define what it means to be equivalent. Two circuits are said to be equivalent if they have the same voltage-current equations at a specific pair of terminals. Also need to define two more terms that we're going to be using in equivalent circuits. The first term is called series and the second is parallel. Two or more circuit elements are said to be in series if they have or carry the same current. And two or more circuit elements are said to be in parallel if the voltage across these elements is the same. So we share the same current, they'd be in series, share the same voltage, they'd be in parallel. This will be our first property dealing with equivalence. If K resistances are connected in series, the equivalent resistance is the sum of the K resistances. In other words, if you had a circuit and you pull out of that circuit a combination of resistances that share the same current, you could replace all of these resistances with a single resistance whose value is the sum of the resistances. Okay, why would this be true? Let's take a look at this circuit with the series resistances. The rest of the circuit here, let's assume, produces a voltage, and the current would have to come out of this box and return because these resistances can only absorb power. So this would have to be generating power. Let's assume that the voltage here is V sub S and the current is I sub S and it comes back this way. Kirchhoff's voltage law. The rise in voltage would be V sub S and the drop be the current I sub S times R1 plus the drop I sub S times R2 and keep on going until the last resistance I sub S times R sub K. Pull out that I sub S term. God is the summation of the resistances. If we now define that as R equivalent, as far as this box goes, if I connect up these K resistances, apply a voltage here from my rest of the circuit, a current will flow. It's on Ohm's law. So the current would be the voltage divided by this total resistance. We also then replace that box with just the value of R equivalent, same voltage, we would get the same current. Current again would be V sub S divided by R equivalent, which we made equal to the sum of these things. That's the proof of a property of series resistances. Next is the parallel resistance property. If we have K resistances connected in parallel, the equivalent conductance is the sum of the K conductances. Okay, what this is saying is that if I have a circuit and I've got K resistances in parallel, unless they're sharing the same voltage, I could replace this by an equivalent resistance whose value is the sum of the conductances, reciprocal. Conductance and resistance have a reciprocal relationship. You can write that this way. If you add up 1 over R1 plus 1 over R2 through 1 over RK, that would be some equivalent conductance, and then if you wanted the resistance, just take the reciprocal of that. Now, why would that be true? Take that circuit and put these parallel resistances in a box. And again, the rest of this circuit is going to be creating a voltage. And the current would have to come out of the box again because this can only absorb power. Let's solve for the current I sub S. Well, it's going to be equal to the current in the resistance R1, R2, R3, R4 through I sub K. What is that current? It's equal to the voltage across it divided by the resistance. Likewise for I2, it's V sub S over R2, and then all the way down to V sub S over R sub K. What's common here now is the V sub S term. God is the summation of the conductances, and the reciprocal of the individual resistances. Let's call that sum G equivalent. Okay, so now if we take this box and put here this resistance 1 over G equivalent, then for a voltage produced here and the same produced with this connected to it, we produce the same current. Again, by Ohm's law, the current would be the voltage divided by the equivalent resistance. It's a proof for parallel resistances. The equivalent resistance, when you have things in parallel, is algebraically sometimes pretty intense. There's a couple shortcut techniques that we can use, and one of them is just looking at the case of only two resistances in parallel. Take a look at what that means. This is the symbol from geometry of just two straight lines to indicate parallel. Just take this last formula and suppose that we have only two resistances. Multiply the numerator and denominator by the same term, in other words, multiplying by 1. If I pick that to be R1, R2, then I have an R1, R2 left over. And then I have R1, R2 divided by R1, which is just R2. And then I have R1, R2 divided by R2, which is just R1. What you got is the product over the sum of the resistances. Now this only works for 2 in parallel. You could take this idea and apply it to something like 3 in parallel. Take 2, use this formula, reduce it to a single resistance, and then do it again with the third resistance. We'll look at examples like this later in the chapter. Another interesting case is when the two resistances are equal. In other words, in this last example, if R1 equaled R2, then I'd have R1 times R1 over R1 plus R1, which would be R1 squared over 2R1. R1's cancel and I get half the resistance. This is very handy when you're trying to make larger wattage resistors. Suppose that I needed a 1 watt 1000 ohm resistance. Take two half-watt resistors that were 2000 ohms apiece, put them in parallel. I would get an equivalent resistance of 1000 ohms, but I now would have the ability to dissipate half a watt in each resistor, so a total of 1 watt. Also carry this idea to the kth case, and that is to have k resistances all equal in parallel. Going back to our definition, it'd be 1 over R1 plus 1 over R1 plus 1 over R1 k times. So we have k over R1, in other words, R1 divided by k. And of course, this is a special case of that. Circuits and electronics, we have to do a lot of approximations because we're dealing with numbers that are very large and very small. This next section deals with the idea of approximation. Before we do that, let me introduce another property. I have k resistances in parallel, then the equivalent resistance is smaller than the smallest resistance of the parallel combination. Okay, so let's just say, take our general definition of R equivalent, sum of the reciprocal of all the resistances. Suppose that this resistance, R3, was the smallest resistance of the k that we're putting in parallel. Let's pull that out of the equation, and so I just have a 1 where I had the 1 over R3. I don't have an R3 in this term, so I have to put 1 back. So when I multiply this out, I get 1 over R1, 1 over R2 through 1 over RK. Is that less than R3? I don't know yet. Let's see if we can do a little more algebra here. Take the reciprocal of this and write this as R3. And then let's divide both sides of the equation by R3. What I've got then is 1 divided by these ratios plus 1. Is that less than 1? Well, yes it is, because I'm taking 1 and dividing it by a number that's bigger than 1. Where this is handy is when you take parallel combinations and maybe you make an algebraic mistake. You can look at the answer and say, okay, this doesn't seem right. In other words, if you took 1k in parallel with 1k and you got 2k. So you can use it as kind of I call an eyeball check for the algebra that you're doing in a problem. Next idea is dealing with approximation. If two resistances are in parallel and one resistance is 100 or more times larger than the other, then the parallel combination can be approximated as the smaller of the two resistances. This is kind of a special case of the previous property we just looked at. Now, why would that be true? Let's let R1 be 100 times R2. Then the parallel combination would be the product over the sum, and you could factor out then an R2 and an R2, and you get 100 times R2 over 101. So what you've got is 0.99 times R2. If R2 were 1,000 ohms, R1 would be 100,000 ohms, and the parallel combination would be 990 ohms. So if we threw out the larger resistance, what we've got is approximately the smaller of the two resistances. To be accurate to within 1%. So whenever we do approximations, it becomes the decision about what kind of a tolerance in them can you live with. This is the idea of equivalent circuits and approximation.